Welcome to you all to this MOOCs online video course Theory of Yarn Structure. Today we will continue discussion about module 1. It is on fiber, the building block of yarns. If you remember, earlier in this module we talked about the characteristics of individual single fiber, and also we solved certain numerical problems on individual characteristics of fibers. Today we will discuss about the characteristics of fiber blends. What is fiber blends? Often we mix different fibers, say cotton and polyester fibers or polyester and viscose fibers to produce yarns. When we mix two different types of fibers, the fiber mix is often called as fiber blends. These fiber blends are important to achieve functional properties, aesthetic properties, performance of the materials, and also it is done to reduce the cost of materials. So, blending of fibers is a very important component in yarn manufacturing process. How to characterize such fiber blends is basically the learning objective of this module. Let us consider that there are m number of fiber components or types to be mixed. M subscript, there are, let us consider this as n number of fiber components to be mixed. It is a very general situation. Now, the total mass of fiber blend is small m. The mass of ith component in the blend is m subscript I. It is therefore evident that if we sum all these ith component where I from 1 to I is equal to n, we will obtain the total mass of the blend m. Right. Now, we will consider certain characteristics of individual components, and also we will try to derive the expressions for those characteristics of the fiber blend. Whenever we will talk about certain component, we will use the subscript. In the symbols where you do not find any subscript, those indicate the characteristics of the blend. So, suppose L subscript I, this is the length of ith component fiber. When we will use L without subscript, that will be denoting length of fiber blend. Now, here this L subscript I actually denote the average length of ith component fiber. To be very precisely speaking, this is the average length of ith component fiber. Similarly, precisely small l denotes the average length of fiber blend. Similarly, T subscript I will denote the average fineness of ith component fiber. And T will denote average fineness of fiber blend or fiber mix. Similarly, rho subscript I denotes average density of ith component fiber, whereas rho denotes average density of fiber blend. Similarly, S subscript I denotes average cross sectional area of ith component fiber. Similarly, S denotes average cross sectional area of fiber blend. This is how we will use the symbols. First, we talk about mass fraction of fibers in the blend. Sometimes we call it as mass proportion. The mass fraction of ith component of fibers is denoted by G subscript I. How do we define G subscript I? G subscript I is defined by the mass of ith component fiber divided by total mass of the blend, right? And the total mass of the blend can be written as this. So, what will be summation of all mass fractions will be equal to 1. Often in textile industries we mix fibers in terms of mass fraction or mass proportion. Also it can be expressed as percentage, say for example G subscript I when we wish to express it in terms of percentage, then suppose this is your kg, this is your also kg multiplied by 100. So, in textile industry we sometimes hear 67% cotton fibers and 33% polyester fibers are mixed. That means here G for cotton fiber is 67% and G for polyester fiber is 33%. As mass or weight is easy to measure, we often in industry go by mass fraction or mass proportion. However, there could be possibility of volume fraction, length fraction, number fraction. We will discuss them in this module. Now we will discuss one important characteristics of blend that is known as mean fiber density, that is rho of blend. It is known that volume of ith component fiber V subscript I is equal to mass of ith component fiber divided by density of ith component fiber. What is M subscript I? M subscript I is M into Gi. So, the total volume of fibers in the blend is equal to V, which is equal to summation of V subscript I when I is equal to 1 to n, that is equal to M into Gi by rho I. M is a constant, it can come out of the summation. So, we obtain M subscript Gi by rho I. Please remember that this subscript starts, this summation starts from I is equal to 1 to I is equal to n. So, we can now the mean fiber density we can write of the blend is total mass of fibers in the blend divided by total volume of fibers occupied in the blend. So, V is equal to M times the summation. So, what we obtain? We obtain 1 by summation Gi by rho I, where I varies from 1 to n. What we see is that the density, the mean fiber density of the blend is not an arithmetic mean, not a geometric mean. However, it is the harmonic mean of the individual component fiber densities weighted by mass fraction of the fibers in the blend. Now, we talk about volume fraction. We know about mass fraction. Now, we talk about volume fraction. Volume fraction is defined by the volume of ith component of fibers divided by the total volume. Now, what is the volume of ith component fiber? We have just now derived this expression. What is the volume of all fibers? that also we have just now derived m into some summation gi by rho I. So, what we obtain? We obtain gi into rho by rho I. So, if we write in terms of percentage, we can also find out similar expressions. So, this is the expression for volume fraction of fibers in the blend. So, by now we know about two fractions or two proportions, one is the mass fraction, second is the volume fraction. Now, we come back to another important characteristics of the blend is the mean fiber fineness. How to find out the mean fiber fineness of the blend? Suppose the total length of fibers of ith component is capital Li. So, capital Li denotes total length of all fibers of ith component. So, what is this total length Li? Total mass divided by fineness of individual component fiber. So, the total mass of ith component is m subscript I and the fineness of ith component is this. Now, what is m subscript mi? M into gi. So, m into gi by Ti. What is the total length of all fibers in the blend? Capital L without subscript, that is equal to summation L subscript I, where I from 1 to n. So, summation m into gi by Ti, I is equal to 1 to n. This m is a constant. So, we write gi by Ti. Now, what is the mean fiber fineness? T. What is fineness? Mass per unit length. What is the total mass? M. What is the total length? L. So, T is equal to m by L. What is your L? L is m gi by Ti. So, gi by Ti, I is equal to 1 to n. So, here again we see that the mean fiber fineness of the blend is the harmonic mean of the fineness of individual components weighted by mass fraction of the fibers in the blend. Now, we go for another characteristics, that is mean fiber cross sectional area. Mean fiber cross sectional area. Now, we have just now obtained T is equal to gi by Ti. If you remember from this module 1, fineness is related to cross sectional area and density of fiber. How is the relation? The relation is fineness is equal to cross sectional area multiplied by density. So, we can write this we can write in terms of volume fraction into rho I by rho. So, this rho is going there and then this gets cancelled. So, what we obtain volume fraction divided by cross sectional area of ith component. So, what is mean fiber cross sectional area? Mean fiber cross sectional area is equal to T by rho. What is T? T is mean fiber fineness of the blend. What is rho? Mean fiber density of the blend. Now, if we substitute rho divided by volume fraction by cross sectional area, and what was rho? Let it keep it as rho. So, this rho and this rho will cancel out. What we will have? We will have 1 by SI. So, here again the mean fiber cross sectional area is equal to the harmonic mean of the individual components cross sectional area weighted by the volume fraction, not by the mass fraction. Now, we come to mean equivalent fiber diameter. We will use this expression. We have just now derived that the mean cross sectional area of fibers in the blend is 1 divided by volume fraction by the individual cross sectional area. What is this S? S we can write as pi d square by 4, where d is the mean equivalent fiber diameter in the blend, which is equal to 1 by volume fraction and SI pi di square by 4. So, we can write down that d square is equal to 1 by summation volume fraction by di squared. So, square of mean equivalent fiber diameter is equal to 1 divided by summation of volume fraction of ith component by square of fiber diameter of ith component. If we take the square root, we obtain mean equivalent fiber diameter 1 divided by di squared. So, this is the expression for mean equivalent fiber diameter in the blend. Now, we come to length fraction of fibers in the blend. Earlier, we came to know about two fractions, one is mass fraction, second is volume fraction. This is the third fraction, length fraction. A blend can be characterized not only by mass fraction, which is typically done in industry, but also by volume fraction, length fraction, number fraction, and so on. What is length fraction? Length fraction we denote by this symbol, which is equal to total length of all fibers of ith component divided by length of fibers in the blend. What is L subscript I? M GI by TI. And what is L M GI into TI, right. So, this is your T. So, we write down GI T by TI. So, if we know mass fraction of ith component, if we know fiber fineness of ith component, if we know the fineness of fibers of the blend, we will be able to know about the length fraction. So, this is how we can also obtain about the length fraction. Now, we discuss about another important characteristics of the blend, that is mean fiber length. What is the mean fiber length of fibers in the blend? Mean fiber length, to derive mean fiber length, we have to know about number of fibers of ith component. Let us consider n subscript I denote number of fibers in ith component of fibers. Right. How we can find out n subscript I? This is equal to total length of all fibers of ith component divided by length of one fiber of ith component. So, total length of all fibers of ith component divided by length of one ith component fiber, capital Li by small li. What is capital Li? We have derived m into Gi by Ti, and this Li will be there. So, we can further write m by Li into Gi by Ti. What is Gi by Ti? Look at this expression. Gi by Ti is equal to lambda I by T. So, m by L subscript I, Gi by Ti is lambda I by T. So, what is total number of fibers available in the blend? Capital N is equal to n subscript I. Remember, this summation is from I is equal to 1 to n. So, what is n subscript I? M divided by Li lambda I by T. This m and T are related to the fiber blend. So, this can be coming out of the summation lambda I by Li. Okay. Then what is mean fiber length? Mean fiber length is total length of all fibers in the blend divided by number of fibers in the blend. What is total length of all fibers in the blend is capital L. What is total number of fibers in the blend is capital N. So, now we substitute capital L. Capital L is m by T. M is mass of all fibers in the blend, T is average fineness of fibers in the blend, divided by capital N. We have to write this expression. So, m by T lambda I by Li. So, this m by T cancels out. What we have is 1 divided by lambda I by Li. So, if we know mass fraction of ith component fibers, if we know fineness of ith component fiber, if we know the average fineness of fibers in the blend, we can find out length fraction. If we know length fraction, if we know individual length of ith component fibers, we will be able to find out mean fiber length. Right. Then we come to another important fraction, which is number fraction. This number fraction is often termed as relative frequency. It can be asked like this: what is the relative frequency of cotton fibers in the blend of polyester and cotton fibers? That means you are required to find it out the number fraction of cotton fibers in the blend of cotton polyester fibers. This number fraction, we can use a symbol nu I is equal to n subscript I by n. Number of fibers of ith component divided by total number of fibers in the blend, that is number fraction by definition. Now, what is Ni? N subscript I we have derived here, m by t lambda I by Li, we write it here, m by t lambda I by Li. And what is n? N is summation Ni, so summation m by t lambda I by Li. This m by t can be cancelled, so lambda I by Li. L, if we substitute lambda I L by Li, right. So, in this way we obtain the number fraction, relative frequency of fibers in the blend. So, what we used here, we use the expression from the last page, L is equal to mean length fiber length is equal to total length of all fibers in the blend divided by total number of all fibers in the blend. This capital L is equal to mass of all fibers in the blend divided by fineness of a fiber in the blend, so m by t. This capital N we derived from here, so this m by t and m by t cancel out, we obtained, this summation should be there, so lambda I by Li. So, this we substitute here to obtain this expression. So, if we summarize, by now we obtained expressions for 4 fractions. One is mass fraction Gi, second is volume fraction Vi, third is length fraction, fourth is number fraction. Nu I. Although typically in textile industries we talk only about mass fraction, because simply mass or weight is easy to measure, you require simple a weighing balance. However, theoretically it is possible to calculate volume fractions, length fractions, number fractions as well. You have just now seen these fractions are important to find out mean characteristics of fibers in the blend. What are the mean characteristics of fibers in the blend we have obtained? Starting from mean fiber density we obtained. So, this was the expression for mean fiber density. So, this was related to fiber blend. So, this is a characteristics of fiber blend, mean fiber density. So, we obtained expression for mean fiber density. Then we obtain expression for mean fiber fineness. This was the expression for mean fiber fineness. Mean fiber fineness. Then we obtain expression for mean fiber density. This was the expression, mean fiber density is already obtained, mean fiber fineness is obtained. Then we obtain expression for mean fiber cross sectional area. All are the harmonic means of individual component. The difference is here it is volume fraction, not mass fraction. So, mean fiber cross sectional area was the third characteristics of the blend we obtained. Afterwards, we obtained another characteristics of fiber blend, mean equivalent fiber diameter. So, this was the expression for mean equivalent fiber diameter. Here also it is the volume fraction. Mean equivalent fiber diameter, and the last one we obtained is mean fiber length. So, mean fiber length is this expression, but here this is length fraction. So, you see all the fractions are somehow important to derive the characteristics for fiber blend. Mean fiber length. So, we obtained 4 fractions and we obtained 5 characteristics of blend. So, a blend can be characterized comprehensively in terms of these 5 characteristics: mean fiber density, mean fiber fineness, mean fiber cross sectional area, mean equivalent fiber diameter and mean fiber length, as well as in terms of these 4 fractions: mass fraction, volume fraction, length fraction, number fraction. Now, what we will do, we will now apply whatever we learned by now with the help of one numerical problem. In that way, we will characterize comprehensively a fiber blend. So, we have our 6th numerical problem. Consider a bicomponent fiber blend. Bicomponent fiber means it consists of 2 components. Tricomponent means 3 component. Monocomponent means 1. So, it is a bicomponent fiber blend which is consist of 40% cotton fibers by weight. So, G1, if we consider 1 stands for cotton, 2 stands for polyester, then G1 is 0.4, G2 is 0.6. You see G1 plus G2, it must be equal to 1 and it is 1. The average properties of individual fiber components are mentioned below. Let me tell you the average characteristics. Say fineness, cotton and polyester. Cotton is fineness in terms of decitex 1.5 and polyester 1.7. Then we talk about length in terms of millimeter. Cotton, the length is 28 mm, polyester you consider 40 mm. Density in terms of kg per meter cube. Cotton you consider 1520, polyester you consider 1360. So, these 3 characteristics let us consider. These 3 are the basic characteristics which are often known in practice. When we mix 2 fibers, say cotton polyester, we generally know their length, we generally know their fineness, their densities are also well known. Based on this, and also given is mass fraction, it is dimensionless, it is given here 0.4 and this is 0.6. These 4 data are given. What you have to find out? You have to find out these characteristics of the blend: average fineness of the blend, average length of the blend, average density of the blend, average cross sectional area of the blend, average diameter of the blend. 5 characteristics I told you earlier, and mass fraction is given. So, remaining 3 characteristics of fractions: volume fraction, length fraction, number fraction. So, let us solve this problem. Whatever formulas we learnt, we will use them directly. So, we start with fineness of blend T. We have learned that T is related to individual component by this expression. Now, all values are given in this table. G1 is 0.4, G2 0.6, T1 1.5, T2 1.7 decitex. So, 1 divided by G1 is 0.4 and T1 is 1.5 plus G2 is 0.6 and T2 is 1.7. So, this value will come in decitex. What will be the value? This can be calculated as decitex. So, we obtain our first answer. The mean fineness of fibers in the blend is 1.614 decitex. Now, we calculate mean length L. What is the formula we have learnt? Mean length of fibers in the blend is 1 divided by length fraction by individual component length fraction. Now, what is lambda I? Lambda I is Gi T by Ti, right. So, lambda 1 for cotton, G1 T by T1. What is G1 given? G1 is 0.4 into T is 1.614 and T1 is 1.5, dimensionless. What will be its value? Its value will be 0.43. lambda 2 will be of course 1 minus 0.43, so 0.57. It can also be calculated in another way, lambda 2 G2 T by T2. What is G2? 0.6 into T is 1.614 and T2 is 1.7. You will see it will also come 0.57. So, this is your lambda 1, lambda 2. Now, we will use this formula directly, 1 by lambda 1 0.43, and what is the length of fiber given? Cotton L1 28, polyester L2 40 mm. So, 28 plus 0.57 by 40, this unit will be in millimeter. So, this value will come approximately 33.77 millimeter. Now, we will calculate mean fiber density, rho. What is rho? Rho is 1 by summation Gi by rho I. We have derived this expression, 1 by what is G1? 0.4, 1520 cotton fiber density, polyester 6. What is this value given? It is given 1360 kg per meter cube. So, we substitute 1360 kg per meter cube. What will be the unit? Kg per meter cube. If you calculate, you will obtain 1420 kg per meter cube. So, this is our third one. Now, we calculate the fourth one, mean fiber cross sectional area, S. What is S? S is equal to 1 by summation volume fraction by individual this. Now, what is volume fraction? Volume fraction is equal to mass fraction, mean fiber density, individual fiber density. Now, so let us calculate V1 first. G1 is 0.4 cotton, this is 1420 and cotton fiber individual density is 1520. So, what is the volume fraction? Volume fraction is 0.37. This is the volume V1, right. Now, V2 is equal to 0.6 into 1420 divided by 1360. So, this will be coming roughly equal to 0.63. So, we have already now calculated this volume fraction, right. We need to calculate now S subscript I. What is S subscript I? S subscript I is Ti by rho I. So, what is S1? S1 is T1 by rho 1. Now, T1 is given as 1.5 decitex T1, T2 is 1.7 decitex, and rho 1 is given 1520 kg per meter cube, rho 2 is given 1360 kg per meter cube. So, if we use this expression, then and if we make the unit balance, then you will see the value will come somewhere 98.7 into 10 to the power minus 6 millimeter square. Similarly, for S2, T2 by rho 2. So, if we use T2 1.7 decitex, rho 2 1360 kg per meter cube and make the unit balance, then this value you will get as 125 into 10 to the power minus 6 millimeter square. Now, we know all 4 quantities, we will be able to calculate S. Let us do that. So, S is equal to 1 by V1 0.37 divided by area 98.7 into 10 to the power minus 6 plus V2 0.63 and 125 into 10 to the power minus 6. What will be the unit? Unit will be millimeter squared. So, if you calculate, you will say this value will come millimeter squared. So, this is the fourth important characteristics of the blend. We are remaining with the last one, mean equivalent diameter. So, mean equivalent diameter is 1 by square root of Vi by di square. So, this is known, but di is not known. What is di? Di is root over 4 Ti by pi into rho I. Suppose d1 is equal to 4 T1 by pi rho 1. So, let us calculate this 4. What is T1? T1 is 1.5 decitex, so 0.15 tex, and rho 1 1520 kg per meter cube. So, this unit will come in millimeter. So, what will be the value of D1? 0.011 millimeter. So, 11 micrometer. So, this is D1. What is about D2? D2 similarly 4 T2 by pi rho 2. So, 4 into 1.7 decitex is T2. So, 0.17 decitex pi into 1360 millimeter. So, this value you will see as 0.0126 millimeter. So, 12.6 micrometer. So, now you know all 4 quantities V1, V2, D1, D2. You will be able to calculate D. D will be equal to 1 by square root of V1. V1 was 0.37, D1 square. D1 square is 0.011 squared plus V2 63, D2 square 0.0126 square in come in millimeter. So, this value will come 0.119 millimeter, that is equal to roughly equal to 11.9 micrometer. So, this was the fifth characteristics. We obtained about the fractions, mass fractions and volume fraction. Also, we obtained about the length fraction. Length fraction was here. So, we are remaining with the only one fraction, that is your number fraction. Number fraction we use the formula nu. We know length fraction into L by individual length. So, nu 1 is lambda 1 L by L 1. You remember lambda 1 was 0.43 here, lambda 1 0.43, lambda 1 0.43, lambda 2 0.57. We use these two values. 0.43 into mean length. Mean length was 33.77 millimeter and L1 cotton fiber length was given as 28. So, this value will come 52. Similarly, nu 2 lambda 2 L by L2, lambda 2 was given as 0.57, was obtained as 0.57, this is 33.77 and length of polyester fiber was given 40. So, this value will come 0.48. This was our last one. So, so mass fraction was given, we obtained length fraction, volume fraction and number fraction, and we obtained mean fiber diameter, mean fiber cross sectional area, mean fiber density, mean fiber fineness and mean fiber length, all characteristics we obtained. So, in this way we can characterize a fiber blend comprehensively. So, this completes module 1. Thank you very much for your attention.